Hello learners, welcome to the next session of quantum computing. So in this session we are going to discuss about quantum autoencoders. So the first section is about quantum autoencoders, and the next is operational mechanism, and third is main components of quantum autoencoders, and the last is swap test in quantum autoencoders. So in the case of quantum autoencoders, quantum neural network are designed to compress the quantum states into lower dimensional representation. When we are going to lower dimensional representation, we can preserve the essential information and sufficient storage, and we can easily process the quantum data. Next, they can classical autoencoder concept to quantum computing by leveraging the quantum circuits for encoding and decoding operations. Next is core architecture. The first layer is input layer, receives quantum state get psi with n qubits. Second layer is bottleneck layer, compress the state to n minus k qubits, and here k discarded qubits become ket 0 vector product of k post encoding, and the output layer reconstruct the original state through decoder Hermitian encoder mechanism also to be. Next, in the operational mechanism, we are checking with the encoding. So here we are going to apply with unitary transformation u of theta to input state of considering all k qubits. So ket psi sub of all components equals trace sub k of u of theta acting on ket psi. So in the case of decoding, we can also go with reverse encoding with u dagger of theta uncompressed state of k qubits. So this is about the Hermitian conjugate of unitary encoding operator of u of theta. Here we are going to think about encoding and decoding mechanism with the help of psi components. So in the case of training, minimize the loss function through state fidelity measurements, classical optimization of circuit parameters, noise robust design for practical implementation. The main components of quantum autoencoder are as follows. The first one is input layer. The input layer receives the quantum state get psi to be compressed. This state typically consists of n qubits. It may also include auxiliary qubits and reference states, which are used later in the circuit for measurement and fidelity checks. The next one is encoder. The encoder is parameterized quantum check u of theta that applies a unitary transformation to compress the input state. It reduces the dimensionality of the quantum state from n qubits to n minus k qubits, where k qubits are discarded into the trash space initialized as ket 0 tensor product of k times. The compressed state is also represented as ket psi components tensor product of ket k components, where ket psi components contains essential information. One is bottleneck layer. This layer represents the reduced dimensional latent space containing n minus k qubits. The discarded qubits hold redundant or non-essential information and are not used as further for encoding process. And the fourth one is decoder. The decoder is another parameterized quantum circuit, typically u of theta, which reconstruct the original quantum state from compressed representation. It operates on the compressed state, and additional k qubits initialized to vector ket 0 ket 0 tensor product k times, aiming to recover the input state with high fidelity. The next is auxiliary qubits. This is to be included in the circuit for the fidelity measurement. It is used in swap test or another methods to evaluate how well the reconstructed state matches the original. And sixth one is classical optimization. The parameter theta of the encoder and decoder circuits using training, and it minimizes the loss function often based on maximizing fidelity between the input and reconstructed states. The seventh one is loss function. The loss function qualifies the reconstruction error by comparing the input and output state. Commonly, it maximizes the and minimizes the trace distance between the states, guiding the parameters and updating during the training phase. And the last one is measurement layer, included of all measurements which are used for computing metrics like different kind of performance metrics to evaluate the phase. And here we are going to check with the swap test of a quantum autoencoder. So swap test in autoencoder, it is very important for verification mechanism to ensure the encoder successfully separates essential quantum information from the redundant data. The core purpose of the swap test is to evaluate or here is discard the trace qubits are in the reference state. After encoding everything, this confirmation ensures that the compressed latent state contains all critical information. The discarded qubits hold no relevant information. So again I am just repeating, the compressed latent state contains all critical information. The discarded qubits hold no relevant data, and that is enabling lossless reconstruction. Mechanism of swap test in autoencoder. First, trash qubits, trash of psi trash, that is output from the encoder's discarded qubits. Reference state, that is a tensor product of, we can go with the tensor product, that is get 0 tensor product k times the desired state of the trash space. And the next is the process. The auxiliary qubit is placed in superposition with the help of gate. Controlled swap gates to be used. A second Hadamard gate is also applied to calculate the auxiliary qubits before measurement. Measurement outcome is the probability of the measuring auxiliary value is 1 plus P of 0, which is equal to 1 plus bra psi trash with the help of ket 0 tensor product k times of square divided by 2. So high value of P of 0, ideally 1, indicates that trash qubits matches the reference state, confirming the successful compression. So what is the cost function here is the swap test P of 0 serves as a training metric. Maximizing it ensures the encoder discards only the redundant information. The next is parameter optimization. Here, classical optimizers adjust the encoder's parameter to minimize the reconstruction of error. So, guided by the swap test results also. So, here we have the implementation of with the help of libraries. So, device is also initialized and apply the parameterized compression unitary. Return expectation volume to value also to be implemented. Simulate over a range of parameters and plot the matrix with the help of visualization graph values. So this is about the output quantum autoencoder versus theta. Here theta, the parameter of RY gates are also to be introduced. So this is about the expectation value and predicted value and actual value. So thank you learners. Thanks. We will see in the next session.